Hi, welcome to our Calculus 2. We are studying a new section today on infinite series. So it's going to be an introductory talk about what series are. By now we have studied what's a sequence. So we have the concept of infinite sequence. Infinite sequence, we write it, for example, like this. What's an example of infinite sequence? So let's quickly write something like 1 over 2 to power of n. What does this generate? A set of numbers. If you start your n at 1, it's 1/2, 1/1/2 squared, and 1/2 cubed, and 1/16. And the fact that it's infinite, the list keeps going. Okay, we have infinitely many numbers in front of us. What do we do with them? Well, there are many things we can contemplate about doing with these problems. The simplest thing would be to add them up, like creating a total for all of these. In that case, we create something called infinite series. Infinite series for an infinite sequence. So what we get when we attempt to add them up, so we write it like sum of, so this big sigma letter, and then the term of this sequence in some index, and then we indicate where the index starts at, typically at 1, sometimes at 0, and then we, for an infinite series, we always go all the way to infinity. And we read this as sum of a sub n, n starting at 1 and going to infinity. So in this case, we are investigating what would happen for this sequence of 1 over for this sequence of 1 over 2 power of n. We are investigating what happens if you attempt to add them up. Well, investigating meaning what? First of all, does it make sense? Does this sum add up to something specific? Or is it that it's not going to behave nicely? And the two cases are labeled as convergent and divergent, as we are going to see. So a big issue for this chapter is, given a series, decide does it converge or does it diverge. In either case, perhaps provide more detailed information as to why does this thing happen, at what rate does it happen, and so on. What is our favorite way of investigating this problem? Well, we break it down to small pieces so that it becomes manageable and also resembles something that you have done before. And that concept now is a concept of partial sum of a series. So we have the concept of partial sum of a series. Well, what does that mean? Well, your series starts at number 1 of the series. Well, that's all by itself. Then you bring in the next one and add the 2 of them. Next one, you contemplate, what if I just pick 3 of them and add them up? So we label these things. Perhaps we call this thing S sub 1, and this one call it S sub 2. This one we call it S sub 3. So this is going to be the first partial sum. This is the second partial sum. This is the third partial sum, and we keep going. So if we come to S sub some large number n, we understand that now. As before, we start A1, A2, A3, and so on we go. And then at the very end, we are going to be adding the last of the a's we have picked, and we are aware that the one prior to that would be a sub n minus 1. So if I'm going to term number 100, I have a 100. The one prior to that is a 99. The one prior to that is a 98, and so on. So I have all of these things listed. Yeah, that forms the S sub n. So this is called the nth partial sum. Well, what's the advantage of this? The advantage is that now I look at this thing and I notice I have another sequence, which is the sequence of these numbers. So I have something I can call a sequence of partial sums. So I had a S1, then I had the S2, and then I had the S3. I can consider this as a sequence, just like A's were sequence. Now I have S's as a sequence. So this is a sequence of partial sums Sn. Well, now I go back to the previous section and said if we have a sequence, we can investigate, does it converge or does it diverge? Okay, we have a sequence S sub n, and now we say, well, does it converge or does it diverge? That is the main tool we are going to use. So the next question is, does the sequence Sn converge? If it does, we write it like this. We say, so what was Sn? Sn was the sum of all these a's, and as n goes to infinity, what do we get? We get a sum of infinitely many terms. We are going to say sum of a sub n from 1 through infinity converges. And then, well, what if it diverges? Well, then of course we are going to say otherwise. We say the sum of n from 1 through infinity diverges. So instead of saying it does not exist, this is another way of saying it does not exist, but in this context we use the word it diverges. Let's give some intuitive cases that we can easily judge one way or another, or at least we might have some sense about this thing. Suppose I ask you, so here's a simple example. Suppose I say sum of 2 to the power of n, as n ranges from 1 to infinity. And the question is, does this series converge? Well, let's try it out. What are the partial sums? It starts with 2 to the power of 1, and then 2 to the power of 2, and then 2 to the power of 3, and so on. I'm adding larger and larger numbers on top of whatever I had, like this is 2, and then a 4, and an 8, and of course going 16, and so on. Does it add up to any recognizable number? Well, we sense right now that it wouldn't, because we are adding larger and larger numbers, and this is the sum is tending toward infinity. So the answer to this question, does it converge? The answer is no, because the sum that you are trying to calculate goes to infinity. Sometimes sums can go to infinity, sometimes they can go to minus infinity, sometimes they might oscillate between a number and another number. All of these things are example of cases where the sum, we say it diverges. What's an example of something that we might sense that it converges? So here is another question that you might be familiar with. How about sum of 1 over 2 to power of n as n goes from 1 to infinity? Does this one converge? What are we investigating now? 1/2 plus half of that is 1/4 plus half of that is 1/8, or let me write it in the power notation, 2 cubed, and then 1 over 2 to the power of 4, and so on. As we add these things together, what is our sense of what happens? Let's just give a quick indication. We are going to have many tests and procedures later on, but just to get started, let's get a sense what's happening here. So here, let's consider this a real number line. Let's suppose this is 0 and 1, and then I say, well, 1/2 is 1/2 of this. And then what is this one? This is a quarter, which is a half of whatever is left here. From here to here is a half. I am adding half of that. So this was 1/2. This is a quarter. It's just 1 over 2 squared. And how about 1/8? 1/8 is half of what is left here. This is a quarter, this is another quarter, and here I pick 1/8 of this. So 1 over 2 cubed is 1/8 of it. Do you get the sense where we are headed here? So of course it's going to be, next I'm going to add 1/16, which is 1/2 what is left to make it to 1. So as I add these pieces, I see that I'm encroaching toward 1, and I get a sense that this is headed toward 1. So does it converge? Yes. Here we have the luxury of knowing what it converges to. That's not common for the series to actually know what it converges to, but in the simple case we actually have a sense as to what the answer is going to be. We say yes, this series converges, and it converges to 1. Next issue up is the notation that is used. It is common that we use sigma sub n, a sub n, we say n running from 1 to infinity. It is just a traditional convention to use a letter n for counting natural numbers. You could have used another letter, a, m from 1 to infinity, a, k from 1 to infinity, a, I from 1 to infinity, a, j. These are all saying the same thing. N, M, K, I, J, if you wish even one more, a, L, L from 1 to infinity. These are conventional ways of counting the whole numbers, 1, 2, 3, and so on. Of course, I could have used any letter. I could have said AX and AY or AZ, but it might be a little bit disconcerting to have some unfamiliar letters here. So this is a convention that is used. As far as I know, it comes from old Fortran computer language notations, where if you wrote n, m, k, and so on, the program would have automatically assumed that you are dealing with a whole number as opposed to a decimal number. So it's just a convention. What is used, we typically stay to this convention. Sometimes this is referred to as a running index, as if it's running from 1 to infinity. Sometimes it's called index of summation. Sometimes it might be pejoratively referred to as a dummy index. You notice that n is not part of the answer. N is just a counter for us that's helping us to count elements of a list. We are saying starting from 1 through infinity, let's count all of them and attach an index to the entries that we have. So when we are adding, you notice there's no n here. N is just telling us how to count 1, 2, 3, 4, and so on. And for that reason, sometimes they refer to it as a dummy variable. Next, notice it's common that we count from 1 through infinity, but I could have started counting from any other number to infinity, for example, from 2 to infinity, or 3 to infinity, or maybe 0 to infinity. The major choices are between starting counting at 0 or start counting from 1, just like an issue that comes up in many computer languages. What number do you start counting at? You see it sometimes in building constructions as well. Is the first floor, or actually first floor, or is it ground floor, and the first floor is the floor above the ground floor, and such things. So those issues also come up in dealing with the series. Do you start from 0? Do you start from 1? As far as the convergence is concerned, it doesn't matter how you label them or where you start at. None of those things make much of a significant difference to the outcome of what we have in mind. Okay, typically you look at series and there are kind of simple expressions, but sometimes a series has in it several simpler series, and for that reason let's go ahead, take a look at another topic, which is making elaborate series from simpler ones. Just like functions, you can construct functions out of pieces. You can also construct series out of pieces. For example, suppose I have a sequence such as 1 over n squared, and then I can have another sequence 1 over 2 to the power of n, and this one gives birth to a series, which is whatever you get from attempting to sum these, and you can also deal with some of these ones, just like what we looked at. Now, if you wish, you can consider a sequence which is made out of adding these, and as a result you will be looking at a series where we are attempting to add these. If you wish, you can make it more elaborate. For example, you can say consider 5 of the first items and say 7 of the second item. And that gives rise to a series which is the same factors show up here. So what are we doing here? What we are doing is creating a so-called linear combination of the series that we have. So if I have one if I have one series which is indicated by sum of a sub n's, like that one, and then I have another series which is indicated sum of some bn, which would be something like this, I might care for creating a linear combination of these two by saying multiply the first one by some number, let's call it r, take the second one multiplied by some number, let's call it, say, well, let me not use the letter s so that wouldn't be misconstrued. Let's say t times bn, and attempt to sum these. Now, if it so happens that some of these terms become some number a and some of this series becomes b, then it's rather easy to show that after you combine them, you will have r of a and t of b. So a series sometimes can be broken down to smaller series, and perhaps they will guide us to an appropriate conclusion about what will happen to the series that we have. Now we come to a certain observation about series, which is a major theorem that is applied in some of the problems that you're going to see. If a series converges, so if I have a series, an attempt to add it, and I come to the conclusion that it converges, what I can conclude is that the terms of the corresponding sequence are getting smaller and smaller and tending towards zero. I can conclude that the limit of an as n goes to infinity is actually zero. Looking at the flip side of this coin, I can say it like this: if limit of an as n goes to infinity is not zero, or it simply does not exist. So if I have a sequence of things, numbers that don't tend towards zero, or don't tend toward anything, then I can conclude that the series diverges. This is a major theorem that we use in some of the basic problems. Let's give a basic example. Suppose I ask you, does sum of, say, n squared over n squared plus 10, summing from 1 to infinity, does this thing converge? Okay, take a short pause, think about it, see if you can use this theorem. So here we have a theorem. Details of this type of theorems you typically see in an advanced calculus class or so-called real analysis class, but it is intuitive enough for us to appeal to it. So pause for a second and come back and tell me what do you think. Perhaps experiment with the terms of this series and make a decision. Okay, so I go ahead and answer, assuming that you attempted to answer this thing for yourself. So let's investigate the terms of the sequence that are building up this series. For example, if I put 1 in this, I have 1 squared over 1 squared plus 10. The next term of it is 2 squared over 2 squared plus 10. Next term of it is 3 squared over 3 squared plus 10. So I don't get a sense as to any easy way of adding these things up, any kind of a formula that's going to tell me what these things are. If I attempt to add them by taking common denominator, I'm going to get some horrible fractions. It doesn't sound promising by going that way. But if I continue this and go further out, what do I see? Suppose I come to say term number 100. I have 100 squared over 100 squared plus 10. What is a quick estimation for this? Quick estimation, I say, well, numerator is 10,000. Well, this is 10,010, 10,010. Well, these are very close numbers, and the ratio 10,000 over 10,010 is very close to 1. This is approximately 1. And as I go further out, like if I consider 101 squared over 101 squared plus 10 and so on, this one comes even closer to 1. As I march toward infinity, the terms of my sequence that I'm trying to add up, each of them comes closer and closer to 1. This is also 1. Next one is also 1. Well, if I try to add 1 and 1 and 1 and 1, well, what do I get? Of course, I'm going to get infinity because I'm adding a substantial amount to whatever I had already. So does this thing converge? Well, from this simple observation, we see that no, it doesn't converge because I'm adding something that is non-zero at the end. I can say no, it doesn't. To make it simple, I say if the terms of the sequence are not approaching 0, then for sure the series diverges. Okay, if it doesn't approach 0, series diverges. Now in this case, the terms are coming close to 1, and I know that my series diverges to infinity, but because I keep adding something close to 1 to it every time. Typically, students read a bit too much into this theorem, and they kind of think that if the terms of the sequence go towards 0, then we are saying it converges. No, that's not what we are saying. We are saying if it converges, the terms go to 0. If the terms don't go to 0, then we know it diverges. So let's see what's a very interesting problem in this regard. So here is a question: does sum of 1 over n starting from 1 through infinity converges? What do you feel? So what do these things look like? 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. Let me abuse your patience and write quite a few of it because I have something in mind. 7, 1, 8 plus 1, 9 plus 1, 10 plus 1, 11. You'll be wondering where does he stop. 113, 114, 115, 116, and so on. Okay. Pretty much everybody thinks, well, I'm adding smaller and smaller amount to this. So it looks like I'm putting a tiny pebble perhaps on top of a pyramid, and eventually it converges to something, whatever that is. Perhaps it looks like it converges. One of the surprising answers here is that no, this doesn't. even though the terms are approaching 0, it doesn't converge. So our theorem doesn't say that if your term gets smaller, then the series converges. No, that's not what we are saying. If you know the series converges, the terms must have been getting smaller and smaller. And if you know it doesn't get small, then you know for sure the series couldn't converge, must have diverged. So how is it that we see here that this thing does not converge? Again, I want to encourage you to pause and investigate by yourself. It could take several days for you to investigate. If you come to a conclusion, then you are definitely a good candidate for pursuing mathematics as part of pursuing a mathematics degree, and we would like to talk to you. But here, let's go ahead and give a quick reasoning why we shouldn't expect this thing to converge. Okay. Well, let's leave this thing alone. This is 1 over 1. Let's leave this one alone also, 1 over 2. I look at the next two terms and say these are each of them at least as big as 1/4. Is that right? 1/3 is more than 1/4. 1/4 is just 1/4. So this is same as this. This is same as this. This is obviously larger than this. This is same as this. What I have in mind is to say, well, when I add these two, 2/4 adds up to 1/2. Next, I go take a look at the next 4 items. We say 1/5 is at least as big as 1/8. This is at least as big as 1/8. This is at least as big as 1/8. Well, this one is 1/8. So it's larger, 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 and this is the same. If I add 4 of these 1/8, what do I get? 4 times 1/8 is 1/2. Do you get the trend? Now what do I do? Add up the next 8, saying what? 1/9 is bigger than the last item of this series, more than 1/16. This one also larger than 1/16. This is larger than 1/16, and so on. These are all larger than 1/16. The last one is equal to 1/16. Well, how many do I have? I have 8, each of them 1/16. If you add them, you get 1/2. This is at least 1/2. It is 1/2. So now what do I have? 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2. And you have the patience, you keep adding. The only thing is that you have to add a lot more terms to make a half. So next one, you start at 1/17, and how far out do you go? Do you see the pattern? How far out do we need to go? Well, if you said 1 over 32, you're on the right track. So the number of terms we add every round is doubling up, but the interesting observation is that what you get is that your series is more than this. And where does this one go? Well, if you keep adding 50 cents to your account all to eternity, that adds up to infinity. What do we conclude? We conclude that this doesn't converge. It diverges to infinity. It adds up to infinity, so it diverges. Okay, so we just started the conversation about infinite series. Let's go back and look at this thing. So we have a sequence. These are terms that are listed, item number 1, item number 2, and so on. Now, one of the things we can do with the elements of a sequence is to add them. When we attempt to do that, what we create is called an infinite series. The notation that we have is a summation notation with sigma, element of our sequence, some sort of running index, could be any letter, start at somewhere and go all the way to infinity. Issue comes up, well, does this thing make sense? Does it converge to anything? Does it do something else? To investigate that, we created the concept of partial sum of series. So we attempt to do this summation a few at a time and see what happens to that. When we attempt to do that, we create another sequence. It's called sequence of partial sums. As a sequence, if this thing converges, then we say our series converges. So if our sequence of partial sums converge, we say our series converge. Example, we gave simple examples of something that diverges, something that converges. This convergence, we gave a geometrical reasoning why the sum of 1 over 2 to the power of n converges. This is perhaps the most significant series you are going to see. It's called geometric series, and I hope that this geometric explanation was easily understandable. Then we said, well, if you have several series, you can combine them. A simplest way of combining them is linear combination, by adding a few of one to a few of the other. So as a major theorem of this section, he said if the series converges, then it must be that the nth term of it goes to 0. Conversely, if the nth term doesn't go to 0, if it doesn't exist or it doesn't go to 0, then the series diverges. Most famous example of that is the series 1 over n, sometimes referred to as harmonic series. It diverges, and here's an explanation of how that happened. Okay, so this was our opening discussion about infinite series, and a much more detailed conversation is going to come up. Until then, good luck and God bless.